Okay, so we're just going to continue with limits and just learn some of the little subtle things that you need to know to be able to calculate left-handed limits and right-handed limits. And if left hand equals right hand, then the limit exists. Okay? And we're going to be doing some step problems as well. And we're going to talk about continuity. Continuity, remember, whenever you draw a graph, if you do not have to lift up your pencil for the entire graph, it is continuous. If you have to lift it up and start at another spot, that is discontinuous. And we're going to see how we can find those out. Now, whenever you're doing a left-handed limit, you will put a minus sign up top on the right, where the exponent usually hangs out. So this is your left-handed limit right there. Okay, we call that the left-handed limit, LHL. Okay, so remember, the complication in mathematics usually comes with just how compact and efficient that it is. But now we're not going to say go find the left-hand limit. You'll just see x approaches a with a little minus sign. Okay, that means go find the left-handed limit. The right-handed limit, you probably guessed already. You're going to have a plus sign here. Okay, that doesn't mean a is positive. In this case, a is positive because of the positive sign that would be there, but not because of the one up top. And sometimes people get that mixed up. So this is our right-handed limit. Okay, RHL. So just to go back, this means we're going to approach from the left. Okay, this means we will approach from the right. Now remember, the point doesn't have to exist. It means it could be a hole in the graph, but if we come from both sides and we get the same number, then that's the limit. Okay, so that was like the hole in the graph. Even though that number doesn't exist, the limit can. Okay? Now, the existence of a limit. The limit is said to, this is a very small blank for this word, exist only if the left-handed limit equals the right-handed limit. That is, the function has to approach the same value from both sides. Okay? So, limit as x approaches a of f of x will equal L if and only if the limit of f of x as x approaches a from the left equals the limit as x approaches a from the right of f of x. Okay, that is the mathematical statement for the word statement above. So if it equals the same number coming from both sides, then that would be the limit. Okay, so here, let's do this example to illustrate this. It says evaluate if possible. So it asks find the limit as x approaches -3 from the right, find it from the left, and then find the limit of x equals -3 as x approaches -3, sorry, of x plus square root x plus 3. Now, I want to just sketch the function first, because if you're anything like me, I really like to see what it looks like. Okay, I'm a very visual person, so I need to see what it looks like. If you just tell me about it, I will probably just nod my head like I pretend I know what you're talking about, but I do not probably at all. So this is square root x. So what would square root x plus 3 look like? We would go left 3 units. So it would be over here. So this would be the square root of x plus 3. What would be the x-intercept? Negative 3. Okay? So it makes sense by looking at the picture that it's negative 3 is the x-intercept. So let's do x approaches negative 3 from the right. So here I am going to be going this way with my x. Therefore, I'm going to approach this way. So I'm coming from the right. Now, if I approach it from the right, I could put in, what number would I put in though? If I was really going to try, like what is the number, the most right of negative 3? Negative 2.99, right? So, and that, again, I think the picture does help that because negative 2 would be about there or wherever. So we can say, oh yeah, right, it's got to be greater than negative 3, which is negative 2.99. Now, this one, we actually have, so if we were to put that in, so example, negative 2.9999 plus 3, what would be the answer? So it's 0.0000, which is getting very close to what number? 0. So in this one, we're actually able to put in 3 because it won't give us our negative 3. It won't give us an error, and you'll get 0. Okay, so we can say that as the limit approaches x plus 3, or square root x plus 3, as x approaches negative 3 from the right, it equals 0. Now, what would be an example of a number for b that would be approaching from the left? Yeah, negative 3.00001. What would that give us? It'll give us a negative underneath the square root sign, which means I can't solve it, can I? Or I should say it equals. So, yeah, so it does not exist. So for C, it says, well, what would be the limit of x plus square root x plus 3 as x approaches negative 3? Now, we know that the right-hand limit equals 0. The left-hand limit equals undefined, or so we would say, therefore, limit x approaches negative 3 of x plus 3 does not exist. Since left-hand limit does not equal the right-hand limit. Okay, it's actually that simple.
So the square root method, if you limit, it's like the x-intercept, you approach it from the right, it's always going to be on the right.
No.
No.
Well, a square root, yeah, but you got to be careful too, because I could take that square root and then I could put a +8 on the other side and now start to do a vertical translation on it, and that changes everything. Okay, so evaluate this one if possible. These are always fun, absolute values. Okay, now we've got absolute value of x minus 6 over x minus 6 as it approaches 6 from the left, or from the right, from the left, and then what would it be if it approaches 6? Now, always remember this stuff here. It's absolute value a, and it's just going to be a if x is greater, or a, sorry, is greater or equal to 0. But if a is a negative or less than 0, we're going to have to multiply by negative a to make it positive or absolute. So the way we want to set our absolute value x minus 6 is it's going to be x minus 6 if x minus 6 is greater or equal to 0. It's going to be negative x minus 6 if, oops, I got an if there, so I don't have to write it out, x minus 6 is less than 0. Now we can further calculate this, both of these, because we could, the first one, we could add 6 to both sides, so that's when x is greater or equal to 6. And this would be if x is less than 6. Now, when x approaches 6 from the right, that means we would be falling into this category, correct? 6.00001. So it would just be x minus 6. If it's approaching from the left side, well, now we're going to be negative 5.99. We're going to have to make it positive. Okay, so we're going to be doing that. Okay, so let's do it from the left. Now from the left, or sorry, from the right, plus sign, this will be limit x goes to 6 from the right of x minus 6 over x minus 6. And I clarified that that's now going to be changed to x minus 6 on top because of this statement here. If it is a positive, if it's coming from the right side, I do not have to have the absolute values in there. So the limit as it approaches from the right will equal 1 when your x minus 6's cancel. Okay, now if we do it from the left side, that means we're going to have to write this as the limit of x goes to 6 from the left of limit negative x minus 6 over x minus 6. Oops, forgot to write my, why did I write limit twice? Okay, that would equal the limit of negative 1, which will equal negative 1. So the right-hand limit equals 1. the left-hand limit equals -1. Therefore, the limit as x approaches 6 of x minus 6 over x minus 6 will equal, because left-hand limit does not equal the right-hand limit. Okay, now we didn't do a picture for this one because it's not really a common sense picture, but because I have access to a graphing calculator, let's just kind of see. That just comes with the computer. I didn't take that picture myself. Okay. Okay, so let's see what that would look like. So we got x minus 6 divided by x minus 6. Okay, so there is -6. So it's approaching -1 from the left. It's approaching 1 from the right. Okay, that's why that. So why don't you just draw. Let's just draw that graph so it kind of makes sense even visually. Because one of the things that we have to be able to do is be able to even look at it visually. Okay, so there's two examples where limits don't exist. I think the ones where limits do exist, they're pretty self-explanatory. Just make sure it equals the same. And that's going to be most functions, right? But it's better to do examples with that they don't work. Now, continuity. Okay? This is where you really have to keep the algebraic and the graphing or the visual in the same at the same time, just like we just did. Now, if we have a continuous function, it's a portion of a function is a solid line with no breaks or gaps. It can be said to be traced by a pencil without lifting off the paper. Okay, that's continuous. So here is an example of continuous. Discontinuous might look like this. It's discontinuous at the breakpoint. So if it's continuous, f of x goes to a, it will equal f of a. So if, say, this was the point I'm looking for, if you came from the left and the right, you get the same value. In discontinuous, if I come from the left, I will get a different y value than if I come from the right. Okay, now these rules that you're going to see, you got to know them well. Now, there's 3 conditions that you need to know for something to be continuous. So, f of a is defined. So there must be a dot at x equals a. And I'm going to explain these really well when we do some examples. Now, number 2, the limit at x equals a exists. And what does that mean? That the left-hand limit must equal the right-hand limit. And number 3, as the limit x approaches a, f of x must equal f of a. In other words, number 1 must equal number 2. Or you could say the limit is the dot itself. So I'm going to give you one that, so say you had a limit, right? And we want to know at a. Now this would be f of a. So is the limit defined at a? Yes, it is. Number 2, does the right-hand limit equal the left-hand limit? Yes. Okay, so then, and is the limit, does it equal the dot? Yes. Okay. Now, I guess the challenge in here is to find ones where maybe 1 works, but 2 doesn't work. Or 2 works and 1 doesn't work. Okay? Now, here basically are the 3 conditions summed up again. There must be a dot. The limit must exist, and the limit must be the dot itself. Okay? So, let's do these 3 scenarios. We've got A, satisfy 1 but not 2. B says satisfy 2 but not 1. And C says satisfies 1 and 2 but not 3. Is yours different? Yeah, I know. I got to put that in there. Because that's what's implied. But if it satisfies 1 and 2, just leave it like that, then it's not very challenging. Okay, that would be just like the one I just showed you. Okay, so how are we going to do one where there must be a dot, but the limit does not exist? Okay, so an example might be something that looks like this. Okay, so no, they're both closed. Okay. So there is a dot, it is defined at A, but the left-hand limit does not equal the right-hand. Okay? Okay. Next, we want to satisfy 2 but not 1. So this would be something like this. At A. Okay, so that is left-hand limit equals right-hand limit, but there is no dot there. So therefore, it's obviously not continuous, because you'd have to pick up your pencil, put it back down. Okay, now C is probably the most difficult of all. So it satisfies 1 and satisfies 2, but it doesn't satisfy 3. So first of all, let's make a dot. That satisfies number 1. So at A, right there. So I've satisfied 1. There is a dot at A. Now, how do I want to make the right-hand limit equal a left-hand limit? You could just do something like this. So I have my left-hand limit equal my right-hand limit, but 3 says the dot must equal the limit. And in this case, the dot doesn't equal the limit. So it satisfies 1, satisfies 2, does not satisfy 3. Okay? It's only confusing for about 2-3 months, and then just... Okay, if you thought that was confusing, then we're going to start, I'm going to show you how to do what's called a step function. Now, this step function may or may not be continuous, but it is taking us through, as we go across the x's, it's going to be changing equations on us. Okay? So you got to be very organized here, and you got to be able to keep things pretty straight. Now, what we're saying is, if you want to just start this quite simple, algebraically determine where it's discontinuous. Well, if we were going on our number line, and you can see 0 and 3 are like critical values. It's changing there, right? It's going from one equation to the next to the next. Now it's saying that when it goes from x minus 2, or x squared minus 2, it's going to be using that equation for all x's less than 0. So this is going to be x squared minus 2 all the way up to here, right? Then, from 0, so we're going to be from 0 all the way to 3, we're going to equal the value 1. I guess we can put it like this. F of x will equal 1, and f of x equals x squared minus 2. And then when x is greater or equal to 3, we will be following f of x equals x minus 4 minus x. Okay, I'm just going to move this up a bit so I can actually draw a nice arrow here. Okay, so that's it explained on a number line. So you can see that the only place we have to check for continuity are at 0 and 3. Because it's continuous otherwise. X squared minus 2, it's going to be 1 all the way, and then it's 4 minus x for the other one. Now, let's talk about at x equals 0. We want to find out, is that continuous at that point? Okay, well, rule number one, or condition number 1, says, is there a dot at x equals 0? Okay, so let's write that down. Is there a dot at x equals 0? If that's true, then f of x would equal what? What is the dot there? F of x would equal what? 1. Well, look at x equals 0. It's 1, right? Anything less than 0, there is no dot for that. It's an open dot. Okay, so we got that one. Number 2. Anyone remember what number 2? What was the... Does the limit exist? Or does the left side equal the right side? Okay, so the left-hand side of the limit, oops, so we can just write this as limit of f of x as x approaches 0 from the left. So as x approaches 0 from the left, what would it equal? Well, let's put that in there. So as from the left, we would put it into, I gotta do this, x of, why am I writing limit down there? X squared minus 2 would equal 0 squared minus 2 would equal negative 2. So as we're approaching from the left, it's going to equal negative 2. As limit approaches 0 from the right, it would equal what? Would equal 1. So since left-hand limit does not equal the right-hand limit, limit does not exist at x equals 0. Must be, therefore, must be discontinuous. Okay, so now let's do at x equals 3. Remember our equation, x equals 3 now. Is there a dot at x equals 3? So is there a dot? Okay, so what is it then? What's f of 3? Yep, it's 4 minus 3 would equal 1. So there is a point at, so basically we've got 0.31. Now, does the limit exist? Okay, so aka does the left-hand limit equal the right-hand limit? So left-hand limit, we're going to do that limit as x approaches 3 from the left of f of x would equal what? It would equal 1, right? Because it says from 0 all the way to 3, we're going to equal 1. Okay, next, let's do right-hand limit. Limit as x approaches 3 from the right Here we go. Of f of x equals the limit as x approaches 3 from the right of 4 minus x. Okay, we can substitute it in there to be 4 minus 3, which equals 1. So since right-hand limit equals left-hand limit, the limit as x approaches 3 of f of x equals 1. Okay, so 3, is it continuous at this point? Does 1 equal 2? Does my limit equal the dot itself? Yep. Okay, so does number 1 equal number 2? Yes. Because f of 3 equals 1 and the limit as x approaches 3 of f of x equals 1. So it is continuous at x equals 3. Okay, now the last thing is draw this graph. Okay? So I've got room on the left here. I just want you to write this. You guys can still see yours, okay? So just do an X and a Y. Find a spot. Now we've got our points, right? 0, obviously an important point. Or I shouldn't have put a dot there. So we've got 0 and 3. Now let's go from the left side. The left side, as we're moving left to right, we're going to be drawing the graph x squared minus 2. Does everybody know, we all know what x squared is, so x squared minus 2, we would be moving down 2, correct? So it's going to look like that. So from from infinity all the way to 0. Now, what am I going to put here at 0? Hollow circle. Because that is when it is less than 0. Now, when it equals 0, what does it equal? Okay, so we'll go up to 1, and we'll put a dot there. And what is it going to equal all the way to 3? 1. So we'll come all the way to 3. Now, we would have that, correct? Because from 0 to greater or equal to 0, less than 3, it's going to equal 1. Okay, next it's 4 minus x. Okay, so it may be hard for you to see this, but 4 would be up here, because this is the same thing as x, or negative x plus 4. So really, this is the graph that we're talking about, correct? But do you see that this part of the graph would not be counted? Okay, because, but I'm just trying to tell you, like, how would you graph that without a graphing calculator? Well, you have to know what negative x. That's 4 is your y-intercept, and negative x means you're going down over 1, down over 1, down over 1, right? So that would be this part of the graph. But do you see, actually I should have, I'm going to make this blue because that was for the old one, but for the new graph, I'm going to color that in for that, okay? So if you look, we had, if you come up here and you call this A, maybe, this B, and this C, just so you can, this would be the A part of the graph, the B, and the C. Now that's called a step function because as you are going across on the x, your y's are changing equations. The point should be filled in because of C. C says greater or equal to 3, you'll have this graph. So you totally won't appreciate these until you start doing them yourself, which is a perfect segue for you to start doing them yourself. I still have one person needs to write it.